uh, in a good way. All right, we have everybody. This will be our last session before we take lunch break, and then head for our field trip in the afternoon. So it's a great pleasure to have my colleague here, Dr. Tom Gilray, who is an associate professor as a fellow of ECS at WSU. He joined WSU a couple of years ago. His areas are in programming language, program reasoning, high performance computing. He probably would tell you a little bit about what he does. But last year he spoke at this workshop, and I have invited him to speak again. And this is going to be interesting because it kind of follows up on the talk you heard yesterday on formal methods for software security. Tom would take a pick up from there and talk about correctness and verification, and he has got a nice concept that he calls contracts. He will tell us about that. And if you have questions, you can ask him at the end. But thanks, Tom, for coming and sharing our students here.
Absolutely. Nice to see you all. So I'm an associate professor here in the ECS department, and I regularly teach the compilers class, which is 452. If you have an interest in taking that, it's a lot of fun. We build a compiler from scratch. We do a lot of functional programming. We kind of go end to end through different aspects of the compiler, and it's very hands-on. I teach 580, which is advanced PL, and then this fall, for the first time, I'm teaching 355. So I don't know if that's undergrad PL. So I don't know if you guys have taken that, but those are classes I'm teaching. And my lab sort of does a lot of work on how do we scale reasoning, especially about complex systems like code. So how do we take a large code base and then really understand formally what it's going to do and implement that kind of reasoning in a very high-level declarative way, and then automatically implement that in a way that can be data parallel and fast and scalable, so using GPUs and coprocessors and things like that. And I think you heard from my colleague Chris yesterday, as Asifa mentioned, and he talked to you guys a little bit about formal methods or something like this. So I'm going to be talking about sort of similar topics. I'll talk about a few ideas that I think are interesting and relevant to what you guys are doing, and that I use in my lab. And then if anybody's interested in these kinds of ideas, I'd be thrilled to talk more with you guys about it in the future. So I'm going to be talking about contracts and this idea of design by contract, and this idea of having a behavioral contract that you can wrap on a component of your software that sort of gives you properties that must be obeyed for that component, right? And sort of defines a notion of correctness. And then how we can use this to actually formally prove correctness, how this can sort of form a bridge towards more general correctness. So as we all know, software is making its way into all aspects of our lives, including in critical situations that are very safety relevant. So there's enormous amounts of C code that has been written for the many processors that are in cars and airplanes. And I'll just kind of mention this probably somewhat old anecdote now of an issue with unintended acceleration, sudden unintended acceleration in Toyota vehicles, right? So as you can imagine, that's quite bad. And when this was investigated, there was a security auditor who looked at all of their code and in court basically testified that it was riddled with bugs and spaghetti-like, right? And probably that doesn't surprise anybody here how that would end up being the case, right? But this is sort of the problem, because how do we get away from this kind of software development where we're doing our best to figure out how to write software that mostly works, but we don't really know if it's correct? How do we get all the way to full correctness, right? How do we really prove that it's correct in as many ways as we possibly can? And I think a lot of this is a result of what's been called worse is better. So this was kind of an idea coined by Richard Gabriel, I think in a blog article of his, and then he's talked about it more. And the idea is sort of that often our incentives are misaligned, so that we're trying to we're sort of trying to produce software as fast as possible that basically works for most of the cases we care about. But in many respects, worse software is actually holistically better for a business, right? Because you can get it out the door faster, you can get it working for most people. The incentives are kind of misaligned, so that often what ends up being better for a business is worse software. And I think part of how this happens is sort of a mix-up between discrete concerns and continuous concerns. Let me try to move this. So often we have discrete concerns and continuous concerns in software development. So I would say discrete concerns would be things like correctness, right? security, robustness. Can the program go wrong in some particular way, right? So that's very binary. It's like it either is correct or it's not, right? There either is a way to exploit the software in a malicious way or there's not, right? And then there's often these soft continuous concerns like, is it simple? Is it intuitive? Is it maintainable for new developers? Is it well commented or self-commenting code, you know? How fast was it to get it to market, you know? Performance and optimization. These are things where, yeah, maybe it could run 5% faster or 5% slower, and neither would be the end of the world. We'd like it to be faster, but there's not really a hard cutoff where it must be a certain speed. Maybe sometimes, but generally that's not the case. Same with things like time to market, right? But often with a business, time to market might be the most important thing, right? So everything is sort of bent towards that, and software is written with that in mind, and some of these discrete concerns may go by the wayside. So worse is better, I think, often comes from a conflation of these two ideas. And it's important in software development to keep our eye on which kinds of concerns really are sort of black and white or binary concerns where we have to ensure that it's correct in some way, right? So one approach to this would be test-driven development, right? And I'm sure this is what you all are mostly using in your own development. You're writing a lot of tests, I hope, right? And trying to make sure that things are correct that way. But of course, tests are under-approximate, right? You're just sort of picking out specific cases and saying, well, will it work in these cases? That doesn't tell you that in general, it's always going to work, right? So it's a great sanity check to write various tests, but no matter how many tests we write, so we can run these tests against the code, but no matter how many tests we write, there's sort of an under-approximation of a broader set of program requirements, right? That really establish that this is doing what we expect and that it's correct and that it's not exploitable, let's say. And so the more tests we add, we're never going to be able to accumulate enough tests to really amount to formal verification. Also, tests are written separate from the code. When we're reading the code, we might not have the tests in hand. Another approach that might be more appealing for many of you and has been sort of advocated by famous computer scientists since the very beginning, right? So people like Dijkstra and Knuth were always sort of emphasizing this idea of mathematically working out on paper what your software should be doing before you even write a line of code. And I think now we're kind of out of that era. That's not going to work anymore, right? You have to be able to develop so fast. Time to market, as I mentioned, is like so important. Nobody's going to come up with a full specification for something on paper before they even start writing the code, even for critical systems, right? We need to be able to sort of co-evolve code with a specification for the code and an ability to prove that the code is correct in some way. So this actually is a full example of Knuth's Runcible compiler on paper. So there's like an example of, you know, what a full specification looks like. So we might want sort of a bridge between these, right? Some way to sort of get ourselves from writing tests to having a full specification, but that dovetails better with some of these continuous concerns that we have, right? That allows us to sort of gradually improve our specification or gradually develop a set of tests that can turn into a full specification. So this is sort of the idea of contracts. So what is a contract anyway? Well, a contract is basically a binding agreement between two parties that's enforceable and where when the contract is broken, you can blame one of those parties for breaking the contract, right? You're not sort of confused about who broke the contract. So to give you an example of what a behavioral contract looks like, let's consider a reallocating array class in C++, right? So if you wrote your own std vector implementation, basically you'd have something like this, an array of elements of type T. And under the hood, you're going to have a pointer to a buffer, which has at least enough room for those elements, right? But perhaps some additional room for adding elements in. So if you want a fast pushback operation, right, like in std vector, you'd implement it this way so it can check to see, do I have enough room to put that new element to the end? If I do, then I just put it in. If I don't, then I reallocate the buffer maybe twice as large, and then I move all the elements in. And so I get good amortized performance because over large batches of insertions, I get good performance, even if occasionally I have to reallocate the entire buffer, right? So when I'm doing this, I may have a precondition that I could assert using an assert statement, right? And so I could say, assert that the length is greater than or equal to the index. Meaning basically that I have enough room for this new index that I'm adding, right? And if I don't, then I reallocate the buffer, copy in the old data, et cetera. So this amounts to sort of one of my preconditions. I want to know that I'm not going off the end of my array, and I want to know that my length is no longer than the buffer length, right? And then I have some insertion with possible reallocation, and then at the end, even though I may have broken some invariant in the middle, I want to return to an invariant that I have. And so I might assert that as a post condition, right? I might say, again, the length is still less than or equal to the buffer length. So if I added a new element and increased the length, the buffer length would also have to have increased, right? So if I add these as assertion statements into my code, what I've basically done is baked in a little hand-rolled contract, right? So the contract is basically something that says, here are properties, preconditions for my component that have to be true when I use this piece of code. And then there are some post conditions that have to be true when I'm done with this piece of code, right? And we're baking that in with assertion. So it actually runs whenever I run this component. And that's basically a contract in a nutshell. A contract is really just a nicer system for being able to do this, right? Where we can sort of declaratively say, here are preconditions and postconditions for my code, and then it gets baked into the code as an actual runtime monitor, right? So this idea comes from Meyer's Eiffel programming language, and he called this approach design by contract, which I'm not sure I'm allowed to use. Probably it's okay here, but it's a trademark term, actually, I think, design by contract. Part of like the Eiffel programming languages branding. And so the idea is that a contract carries these mutual obligations and benefits, and you attach them to different pieces of code. And as long as you're satisfying those contracts, then you can assume that the code should be correct, right? If I call a function and I satisfy the preconditions for the function, well, then the function should run correctly and it should satisfy its postcondition, right? So in the original Eiffel language, it looked something like this. I won't go into this too much detail, but it's like some code that's adding something to a tree, and they had these require and ensure blocks that you would add around your code to say, here are the preconditions and here are the postconditions. So as a precondition, maybe we want to ensure that the node that's being inserted is not void or null or something, right? So that's what we're doing here. Okay, so close that. Okay, so to call put child, we must satisfy the preconditions, and they're going to be dynamically checked. And then if the preconditions are satisfied, then the code should give us these benefits, which is basically that it runs correctly and ensures the post conditions are correct as well. So if we pass it void and do something bad, then the precondition fails, and so then we don't get to run our code, right? It's just going to stop and give us an error. And so that's bad, but at least it's not allowing something worse to happen. It's sort of giving us a definite error and stopping. So it's delaying error discovery until we actually run the code, right? Just like a test. But in a way, it's turning every run of my code into a test, right? So it's sort of a property-based testing that I'm baking into my code so that every time I run the software on any input, when that component runs, that specific execution is basically turned into a test, right? And so then if the code runs, then we know the test passed correctly, or we have an opportunity to realize that something is going wrong. Contracts can be built in a few different ways. So often they're a linguistic mechanism. They're built into the language. Sometimes they're also added using macros. So you could write a library for some languages which use their macro system to add in contracts. In some case, they're a source-to-source translation as well. So this is an example of that for Java. There's a JContract system, which basically lets you add comments to the top of your code, which has these @pre and @post declarators that allow you to basically use a little snippet of code that runs as the precondition check or the postcondition check. So here, n is greater than or equal to 0 for the input to this factorial function is just a piece of code that basically you can think of as being added into an assertion statement, right? So basically, this just adds those insertion statements for us automatically. And then return is sort of a special keyword for this that represents the return value. So what it's basically doing is compiling it into something like this, right? That then checks these preconditions and postconditions when the code runs using assertions. Um, there's also a powerful contract system in Racket, which is a language that I use a lot. So this is sort of a functional programming language based on scheme. They've done a lot of interesting exploration of contract systems. It's kind of a research language. And so this is kind of what it's for, is inventing new language features and experimenting with them and using it as a test bed for experimentation with features like this. It's also been added in via macros to JavaScript. And so this is a contracts.js system. And you can actually play around with this yourself online if you want. So if you just want to get a quick sense of how contracts work and look at some examples, and if you're familiar with JavaScript, then you could take a look at this code. Here's an example of this. Let's say we have a function array num to stir, right? So it takes an array of numbers, and then it's going to give us back an array of strings, right? Converts each of those numbers into a string. So maybe it looks something like this. I don't know if that's a reasonable implementation in JavaScript, but this would work. And here are assert statements around it, right? We might want to assert that the array is, say, an instance of an array. And then when we're done, it's still an instance of an array. And so that's a simple precondition and postcondition. And so basically, this is a little bit like a type declaration, right? That says, well, I have an array of numbers, and I'm converting it to an array of strings, right? And you can think of contracts as basically giving you a more general framework for doing the kinds of things that you would do with types, except you can run arbitrary code as your precondition, and arbitrary code is your postcondition, right? So we're not limited to saying this value has a particular type. We can say things like that, but we can also run arbitrary code to check an arbitrarily sophisticated property. And that's really one of the things that's important and nice about contract systems, is that it allows us to check potentially very sophisticated properties by writing arbitrary code in the host language. So, for example, if we wanted to flesh out this, this type check of it's an array of numbers to an array of strings, then we would have to add in some extra code to our precondition and postcondition to actually check that each of those values is a number. And looks like this is fairly ugly in JavaScript, but that's how it looks, right? Okay. So in contracts.js, we can write it like this, using this at symbol. And this is a macro that basically intercepts this declaration and then adds in those ugly assertions that I just looked at, so we don't actually have to write them ourselves. Okay, what if we wanted to make this a little bit more interesting, and we wanted to allow the user to pass in a formatter function, right? So now this is the function that's taking a specific integer and turning it into a specific string within these arrays. So I give you an array of integers and a function that takes an integer, and then you give me back an array of strings where you've used that function to produce a string for each of those integers, right? So you're sort of mapping this over the array of numbers. So now we have this format function. We're using it on each element. And you can see here's an example. And so, for example, we could pass in a formatting function that converts it to hex if we want, instead of decimal. And so that kind of shows the generality of this. So the problem is, how would we actually expand this to something that's doing a precondition check, right? Now we have to have an array. All the elements of the array have to be numbers. And then also we have to have a function which itself is this number to string function, right? So if that's just a type, then maybe it can be statically type checked. But if that's in general a contract, this is arbitrary code that's being run as a precondition and a postcondition check, right? So we can't really just check that of this function, right? Because how are we implementing these contracts? We're implementing them by adding assertions into the component itself. So it's not until that component runs that we actually see whether or not it's violating its contract, right? The component is being dynamically monitored, and we can't say in general that it's always satisfying the contract. We just have to check as it's running. In this case, does it satisfy the contract? And then in this case, does it satisfy the contract? So again, it's more like testing than true verification, but it's giving us tests for this component every single time we run the code. So the idea here is that we actually have to delay checking of the format function until the format function runs, right? We can't actually check it right at the top of the function, right? Because we haven't run it yet, not right at the top of the array num to stir function. We have to wait till we run the format function. So contracts and behavioral values are delayed. And this is basically how contracts can be elegantly extended to higher order languages that include first-class functions, right? So you can pass a function into another function to parameterize its behavior. But when you do that, the contract on that argument function has to be checked only when that argument function is actually run. So we have to delay that checking, but we still want correct blame when something goes wrong, right? So if I pass array numptester a bad format function, when the format function fails, right, I have to delay the check until it runs, but then if it does fail, I want to blame the caller to array numptester. I don't want to blame the caller array numptester to format, right? I want to blame the original party that actually passed a bad format function in, right? So that's kind of one of the key ideas here behind behavioral contracts for higher order languages. So if we change this to just basically be the identity function, it takes a number and it echoes that same number back out, right? Well, now it's no longer a num2stir function, and so now it's going to fail, but it's going to fail here on this line where we call format. It's not going to fail the moment we call array num2stir, but it's going to give us an error like this, which basically says the calling context for array num2stir is the party to blame. Right? So now, even though that's 2 steps removed, it was still able to track that. And if you have an even more complex situation where you're passing around first-class functions, you can have situations where you have to blame a party that's arbitrarily far apart from where you are, right? And doing that correctly is tricky, and is one of the things that higher order contract systems are doing that kind of gives a lot of extra power. Otherwise, you might be thinking, well, I can just manually add some of these assertion statements in, right? But this gives you the ability to add these high-level declarations of preconditions and postconditions to components and have them work for first-class values, first-class behavioral values as well. Okay, so what are some of the sort of advantages and disadvantages of behavioral contract systems as opposed to static type checking, right? Static type checking has a separate type language with its own static semantics that we have to design for our language, whereas a software contract uses the exact same expressivity as the host language. So as I've said, these precondition and postcondition checks can be arbitrary code in Java or JavaScript or C++ or Racket or whatever it happens to be, right? And these contract systems are basically being added to just about any language. So whatever language you like to use, you probably can find a good contract system for it. As I said, there's source-to-source translations like JContract, there's macro systems. It's also just being added into the specification for languages. So you might not be surprised to learn that even C++ is now adding behavioral contracts to the language. So in C++ 26, you'll now be able to add a pre and post declarator after your signature for your function if you want to add a contract in. Okay, so basically you either have a more restricted type language that you've designed, or you have the arbitrary power of the host language, right? In software contracts, you're reporting actual observed errors with witnesses to errors, right? So you're saying this exact trace fails and here's exactly why and here's the party to blame. Whereas in static type checking, you're reporting potential errors in abstract terms, right? Not necessarily concrete definite errors. With software contracts, it adds significant runtime overhead, right? Because these are dynamic monitors. They're actually running as your code runs, right? So there's some various tricks to making that faster. You could remove the precondition check for recursive functions. Some languages do that. But bottom line, basically, it adds a lot of dynamic runtime overhead. Static type checking is much better in that sense, right? It's all ahead of time. And then also, very importantly, error discovery is delayed until runtime with contract systems, right? You don't get to know at the point where you're writing your code that something is going wrong. You only know once it's running. Now, maybe it's being run on a bunch of tests. And whenever you run it on large integration tests, every component that has a contract basically becomes a test, as I've mentioned, right? But no matter how much you test it ahead of time, there's still the potential to then discover one of these errors in production much later, right? Whereas any kind of static verification or static type system is going to give you ahead of time discovery of these potential failures. So one of the things that I'm very interested in is how do we use these contracts as a bridge to full static verification, right? I think we can sort of view this as a gradual approach to being able to get ourselves closer and closer and closer to having full verification by baking a specification for our program into the code itself, component by component, right? So now the nice thing is it's more like self-documenting code. Instead of having a separate set of tests, we've got the tests and the properties baked into the software itself, right? It sort of documents the properties as you read the code. You could also leave off some properties that are too pedantic or something for certain components and then add them in later. So it kind of gives you a more gradual approach where you don't have to design your specification all ahead of time, right? But also you can build up towards a full specification and you get better and better and better testing of your software as you do that, right? But no matter how many contracts we add, we're never really getting verification. So that's what I want to talk about next, is how do we actually turn this into true verification, right? If we have a specification, like a set of types in a simple case, or maybe the Knuth diagram that I showed you earlier, a full specification of the whole system or something, we might want to be able to take that and then just verify that all of those properties are always satisfied for all executions fully ahead of time, right? But how do we get there in a more gradual way? Well, if we analyze a piece of software, it's rather tricky if we don't know things about how the software works, right? So, whatever ambiguities there are in the software's behavior can kind of ramify as we consider the possible executions of this program. And in general, if you're trying to analyze a complex piece of software in a very general purpose way, what you're kind of doing is simulating the software, right? Just like scientists might simulate something in the real world, say physicists simulating lasers or something using computers, right? It's like, well, it's all software, but still we might use software to simulate other software, right? And that's how we can sort of figure out what's going on and build models of that software. And if we're doing this in the context of a very high level, higher order programming language like JavaScript or Racket or really most multi-paradigm programming languages these days, then we have this problem where when we call a function that may be a first-class function, so here g is being passed into the function f, and then it's being called in the function f, right? What happens to the control flow when we call g on y here? Right? We really don't know if we don't know what the data flow to g is, right? We have to know something about the data that flows to this variable g in order to know when we call g as a function, where do we go in our program? Which component are we jumping into? And which g got passed to f, in turn, depends on the call sites to f, right? So if I have these different call sites to f, then I'm passing in different g's, and my f is going to behave differently, right? So this problem, this entanglement of data flow and control flow in your program is called the higher order control flow problem, right? And so in any language where you don't have a sufficient amount of structured control flow, where you can ensure, say, I have a C program, it's all kind of idiomatically written, there's no function pointers anywhere, so all the control flow is explicit, and I don't really have to analyze the control flow. I can take that for granted, and then I can model data flow as sort of a dependent simulation of that, right? I can take my control flow for granted, and then I can simulate the control flow, the data flow behaviors of my program in a stratified way, right? But with more higher order types of programming languages, we have to simulate these together. So that's kind of the answer. Simulate all the properties of your program that you care about all at the same time and allow them to be mutually entangled. So to do this, we use AI, although not the kind of AI you're thinking of. This is abstract interpretation, although the kind of AI you're thinking of is definitely very relevant and is being used more and more in software development and sort of program testing and verification, right? But it always kind of rubs me the wrong way a little bit when people use an LLM and then just say that it's a verifier, because of course it's not really a verifier, right? It's not giving you sound information about your code, although they can be so excellent at helping you highlight where bugs are, right? And helping you understand your code and point out possible issues. The problem is they're not fundamentally sound. They can't actually give you a guarantee of correctness, right? So what we want to do is build a sound model of our program's behavior that actually makes guarantees about how it'll behave in general across all possible program executions, right? And then maybe we use that model by giving it to an LLM, and maybe it helps us to interpret it and figure out how we actually fix those bugs or something. So So what's the idea of abstract interpretation? Well, abstract interpretation is basically just the idea of developing a simulation of a piece of code from an interpreter for that piece of code, right? So if I can write an interpreter for a programming language, maybe it's a standard programming language, maybe it's a language I've designed or like a little domain-specific language for something, but if I can write an interpreter for it that runs that code, well, then I can use abstract interpretation as a framework for turning that into a simulation of the code that gives you, say, a strict over-approximation of all program behaviors and says, here are the program behaviors it might exhibit, and any others cannot be exhibited, right? And so then that would give you a proof of things the program cannot do versus things that it might do. And in order to do that, you need to be able to reason about the program in sort of abstract or approximate terms, right? And one of the important things is to figure out what's the level of precision that you really need. When you're running a program, you're simulating the program with perfect precision, right? You know exactly what values you're dealing with. You know exactly which parts of the code you're jumping into. With a simulation of the program that's agnostic to a particular execution and that's trying to model all possible executions, well, now you don't know exactly what's happening in your program, right? There might be various places in your program that you are. The variable x might be bound to various different integers. Maybe you know it's an integer, but you don't know which integer, right? And so integer is a good example of an approximation or an abstraction of what your code is doing that doesn't give you perfect precision. It doesn't say it's the number 5, but it tells you something about what the variable x is bound to, right? And so we're trying to figure out what is the degree of precision we need to be able to reason effectively about this program. So we do this all the time as human beings. We're always kind of negotiating the right level of abstraction. So I might say, do you know the way? And you might say, sure, you take a left just past the tree there. And I say, the little poplar just there. And you say, no, the one with 51 branches and 8,200 leaves, right? And that would be way too much precision for what I need to know, right? It's actually confusing me. Probably you would just say, no, the large oak tree over there, right? And so you're trying to pick the right level of precision to be able to communicate effectively, right? And to be able to reason about something. And it's the same thing in simulating software. So all the different abstractions that we're using, we could think of as falling on a lattice of precision, where at the very bottom, we have something that's so precise it can't exist. And at the top, we have something that doesn't tell us anything about what we're dealing with, right? And so, for example, the very top of our lattice might just be thing in sort of casual parlance, right? It's just something, right? And a little bit lower might be tree, but it doesn't tell us what tree. And then a little lower might be large oak tree, right? And way down here at the bottom, it might be a tree with 51 branches, et cetera, right? And so we can think of there being different degrees of precision that we could use to talk about something. And the reason I say this should be a lattice is because a lattice is a partial order, right? So some elements can be compared, some elements can't be compared, where we have a little bit of additional structure that says all pairs of elements have meets and joins, greatest lower bounds and least upper bounds, right? And that's basically to say all 2 points in this lattice participate in a diamond, right? And have a greatest lower bound and a least upper bound. And what we want to be able to do is place bounds on the behavior of our program to say it'll do anything that's within this range of behaviors and nothing else, right? And so that's a bound on program behavior. And lattices give us a way to basically work with bounds on program behavior where we can have 2 different possible bounds on program behavior, and we can basically compute their least upper bound, which basically means the disjunction of those 2 possibilities, right? It's either this or it's this. And that would naturally be the join on the lattice, right? Which says it could be either of those things, but without adding any other superfluous detail that wouldn't be necessary, right? It's the least upper bound. Okay, so we take a program, we can inject it into a representation of the program being run, so an initial state of the program being run, and then if we have an interpreter, we can just iterate a transfer function f that takes one of these program states and then just says, how do I step it to a next state, right? And we can just iterate that process. And this is basically called an operational semantics. So the idea is that we come up with some representation of the execution of our program, we come up with a step function or a transfer function that tells us how to basically take one step of execution, and then we just iterate that, and that gives us an execution trace. And if we zoom in on one of these states, a state might contain something like a program counter, a binding environment, a model of the local stack frame, local variables, a model of the heap. What kind of structures do I have on the heap and how am I approximating them? A model of the stack, etc. Right? These are 4 common components, but whatever is important for your programming language, you might include it in the program state and then use it to model what's happening in your program. And the idea of abstract interpretation is now that we're going to lift this from exact values, which we could also think of as sort of precise bounds on program behavior, to these approximate bounds on program behavior, right? That are somewhere in the middle of our lattice, but that still allow us to pragmatically and productively reason about what our code can and can't do. So let's look at an example of a contract for a simple function in Java and how abstract interpretation kind of applies to this, right? So here's a very simple toy function, next odd, just takes an integer and gives us back the next odd number, right? So it checks to see if it's even. If it's even, well, we just bump it by 1. If it's odd, well, then we have to add 2, right? And you can see here I have a post condition that I've added that says basically it's not even or it's odd, right? So I should be able to give it any integer and then always have it come back with an odd number, right? So how do I prove that? We can all look at this code and see how it works and kind of understand that in fact, indeed, it would always give us back an odd number, right? But how do we use abstract interpretation to reason about that in an automated way? Well, we could use our interpreter and just give it the number 9 and then observe that it gives us back 11, right? And if we tried lots of possible inputs, we might get a better and better sense that yes, indeed, they always seem to be odd numbers coming back, right? But that's this testing approach. And as I said at the very beginning, no matter how many tests we add, we're never going to get to the point where we have full verification that for all possible executions, it's always going to behave, right? Because we can't actually try all possible executions. So we have to be able to reason in an abstract way about this, right? So maybe we think about putting in the set of all integers, right? If we put in more and more integers in the limit, eventually we could imagine putting in the set of all possible integers and observing that we only get back the set of odd numbers. But the problem is we just can't actually materialize all of these inputs and outputs. So instead, we want to use a lattice that represents different bounds, right? So in the simplest case, we could have a lattice of integers and, the power set lattice of integers, so sets of integers, right? And so instead of having a particular number like 9, which is being given to this function, and a particular number like 11 that's coming back out, now we have some bound on the numbers that are being passed into the function, and a bound on the possible numbers that are coming out, right? And the bound that's going in could be the set of all integers, right? And we want to see that the bound coming out is the set of just odd integers, right? So now we're dealing with points on this lattice. This is the power set lattice for integers. So the very top is all integers, right? The very bottom is the empty set. And these points in the middle are specific sets of integers, right? So way down here near the bottom, but not quite at the bottom, we might have the set 3, 4, right? So it could be 3 or it could be 4. Or over here, we might have 1, 2, 3, right? And then again, joins in this case are just set union, right? So the least upper bound for 2 sets is just the union of the 2 sets, right? The minimal set that contains everything that's in either of these sets, right? So now the problem is that, as I've kind of indicated with these ... dots in the middle here, this is an infinitely tall lattice, right? It's countably infinite. There's a countably infinite number of steps to go from bottom to top, step by step, right? So we could accumulate integers into our bounds, but if we're doing it integer by integer, it's going to take us an infinite number of steps. And so this is a way of sort of illustrating the problem with just testing, right? What we want is to be able to jump up to the top of this lattice, right? Or somewhere near to the top of this lattice, where we have something like the set of all odd numbers, right? We're trying to come up with, if I put the set of all integers into the next odd function, the set of all odd numbers comes back out, right? So the set of all odd numbers is somewhere in this lattice, much higher up, but not as near to the top as this. And what we could do is, while we're simulating our program, we could approximate our join, our set union, by just adding in some other integers if we wanted, right? And we can accelerate our path up this lattice. And that's, in a way, the fundamental game you're playing in abstract interpretation, You're trying to say, well, if I voluntarily give up precision, can I gain a bound on the complexity of my analysis? Can I accelerate convergence of the analysis so that it terminates faster? Right? Because this could take an infinite number of steps to terminate, right? So it's not necessarily ever going to terminate. If I want to guarantee termination, maybe I want to guarantee that it's efficient, that it's quadratic or cubic or something, right? Then I need to be able to give up precision in order to achieve that. But how much precision do I give up and exactly how, right? That's the challenge. And so one of the tools that abstract interpretation gives us is this idea of a widening operator. And a widening operator is just the idea that you could come up with some other operator that takes the place of join and that just approximates join, right? It just gives me a value that is no more precise than join would give me, right? Could be the join, or it could be the join with a bunch of other stuff added in. Okay, so for the purposes of this example, what might we want to add into this set to accelerate convergence to, say, the set of odd numbers? Right, let's say we've got the set 3, 5, 7. Right, if we've got the set 3, 5, 7, and I keep putting new integers into my next odd function, I could continue to accumulate new possible integers that could come out of my next odd function, right? 11, 13, 15, et cetera, and I could add these all into my set, but it's going to take me an infinite number of steps to get to all the odd numbers, right? But what if every time I add one odd number into my set, I add all the rest in automatically, right? And every time I add one even number to my set, I add all the other even numbers in automatically. Well, now in one step, the moment I see any odd number, I'm going to jump way up this lattice to a set that includes all the odd numbers, right? The moment I see one even number, I'm going to jump way up this lattice to the set that contains all even numbers. The moment I see an odd and an even number, I'm going to jump all the way to the top of this lattice, right? And have all integers. So now, even though I have this infinite lattice, I really only have a few points on the lattice that I'm using. And that kind of defines an abstraction that's useful for this property that I'm trying to verify, right? It kind of looks like this. It's a lattice that only has the empty set, the set of all odd numbers, the set of all even numbers, and the set of all integers total, right? And so a widening operator would just be a way of basically saying, I can have a simpler, coarser lattice that I'm using for my abstractions, but the problem is I still can't implement it because I can't implement it directly as these infinite sets, right? I have to actually symbolically say this is odd or this is even. And now I can have a finite representation of something which, if I had to spell it all out, would be infinite. So this is the other approach that abstract interpretation advocates for, which is basically to structurally abstract this lattice as a simpler, coarser lattice, which is no longer infinite. And so we can gain a bound on complexity of our analysis because the abstractions that we're using simply cannot grow without bound, right? They cannot grow ad infinitum. Eventually, they're going to hit top in a finite number of steps, right? Because the lattice itself is finite. And so what's required is for us to come up with an abstraction function and a concretization function, which basically relates these two universes. We have a concrete or a precise universe of all the different bounds we could place on our program that's completely granular and precise. And then we have this other universe that's more abstract, right? That says, oh, I really only care about the parity of the numbers, right? Is it odd? Is it even? Is it both? Is it either? That's all I care about. And so I can connect those two. And that basically gives me a way of formally connecting these two kinds of abstractions so that I can use the simpler abstractions while keeping them in a correspondence with the more granular abstractions. So then what abstract interpretation says we can do is to take a concrete interpreter and to plug it together with one of these abstractions, right? Some coarser lattice of values and bounds that I want to track, and come up automatically with an abstract interpreter. And so that sort of looks something like this. The original creators of abstract interpretation, French mathematicians Patrick and Radia Cousseau, basically advocated an approach they called the calculational approach, which basically said you can compute an abstract interpreter from a concrete interpreter and a notion of abstraction. In practice, though, this can be rather difficult. Another approach would be to design an interpreter, an abstract interpreter, and then justify it using these notions of abstraction and concretization. So returning to our example, how do we sort of use this framework? Well, what the framework basically says gives us is a way um, of basically reasoning in a closed form way about operations in our code using these abstractions that we've come up with, right? So for example, if we have odd plus odd, this says you can calculate the best abstract plus as the composition of concretize, then do a concrete plus, then abstract again, right? That's this calculational approach that I mentioned. So what does that look like? Well, we concretize. So instead of having symbolically odd plus odd, we have the set of all odd numbers, or all odd integers, plus the set of all odd integers, right? And then we can reason that any pair of those two would give us an even number. So we get back the set of all even numbers. And then we can abstract again. And because we don't have even a single odd number here, the most precise abstract representative would just be even, right? And so we can precisely say that anytime we add two odd numbers, we get an even number. So this is just a very simple example, right? But this is basically the approach that's being used in abstract interpretation to develop a correct simulation of code from an interpreter, which can kind of give us which we can kind of think of as being an arbitrarily precise analysis, right? A concrete interpreter is just an analysis that's so precise, it's only ever telling us about one exact concrete execution of the program with exact values. And so if we can talk about the program in precise terms, abstract interpretation gives us a way to loosen that precision, give up some precision, but gain a bound on the complexity of our analysis so that it always converges with some answer for us. Okay, so now what we can do basically is, this is sort of just an example for what's happening with numbers and arithmetic, right? But you can build this up piece by piece and put all these components together, and you can turn a concrete interpreter over more complex representations of the program into an analysis over these more structured representations of the program. So now what we can do is we can inject our program into an initial state, take that initial state and abstract it to an abstract state, and then iterate what is now an abstract, closed but non-deterministic transfer function, abstract transfer function, that instead of telling us for a specific input state, what's the output state, instead now it says for a specific input abstract state, what are the 0 or more abstract successor states that we can step to, right? So because we've given up precision, we also have necessarily made this non-deterministic, right? Can we think of a good example of that? Like if I don't have perfect precision in reasoning about my program, why would this become non-deterministic? Maybe I've got something like a conditional statement, right? And I say, if x is less than 2, then go down one branch, otherwise go down another branch. Well, if all I know is that x is an odd number or something like that, well, I don't know if it's less than 2, right? So I have to go down both branches. And that's the idea of being sound and correct when producing an over-approximation of my program behavior, right? If I was to give up one of those branches and not explore it, then it's possible that some real behavior that would be exhibited by the program wouldn't be considered and wouldn't be included in my model, right? So to be a sound, correct over-approximation of my program behavior, I have to consider all possibilities. And so in a case like that, given that we're giving up precision, this becomes non-deterministic. But because these abstract states are now falling on a lattice, which we've made finite, there's only a finite number of these states we could explore. Maybe a very large number, but maybe something that we could say has a bound that's cubic in the size of our program or something like that, right? And then as we're exploring these states, I can guarantee termination, and then eventually we'll produce this closed abstract transition system, right? And the idea of soundness is that every possible actual concrete execution of my program is included in this model, right? So that basically means if I were to take some arbitrary input and actually run the program and come up with an execution, this would always map onto some path through my model, right? In fact, if we just zoom in on one of these boxes, this is basically in the abstract the soundness condition we have to prove, right? That if I have some concrete state which has a successor state, and if I abstract it, and then I use my abstract transition function to take a step in my analysis, then I have to get something, at least, that would model the successor state that I got in my concrete execution. Okay, so to kind of bring this back to contracts, right? I said I wanted to produce a way of sort of giving you a bridge from building up more and more contracts, which sort of tests your code more thoroughly, to actually having a verification of the code, right? Being able to build a model of the code and verify maybe that some of these contracts must always be obeyed. Well, to do that, we're using a combination of abstract interpretation and symbolic execution. So symbolic execution is the idea that we might associate with variables in our program a symbol, kind of a symbolic value, which does denote a particular concrete value, but we don't know which one. And we're going to build up a formula which constrains that value and tells us something about that value by giving us a formula that must be true. And so the idea would be, in this case, that we have this, which we could say is alpha, and then our element, which could be beta, and then our index, which could be gamma. So again, we don't know exactly what they are, but we're going to give them symbolic names. And then when we go through a conditional statement, based on which branch we go down, and again, maybe we're going to explore both branches, right? But depending on which branch we go down, we know something about what's true in that branch, right? So here, if I step into this error statement, right, assert failed, that means that length was not greater than or equal to index, right? So that means alpha.length is less than gamma. Even if we don't know what alpha and gamma are, we know that that must be true down this branch, right? So what symbolic execution normally does is helps us test a program by exploring lots and lots of different paths, building up formulas that represent what must be true down those paths, and then throwing those out to an SMT solver to ask, are those actually feasible paths? Could those formulas be satisfied? Is there any alpha and beta and gamma that would make this happen, right? If this assertion never fails, then that should be false, right? There should be no satisfying assignment to alpha, beta, gamma that would actually make this true, right? So symbolic execution can help us to prune paths that we know are not feasible and aren't as worth exploring, or can give us examples of alpha, beta, gamma that would make something fail. And so it's usually used for testing, but it doesn't give you a way of verifying your code unless we combine it with this idea of abstract interpretation. So if we return to this idea of abstract interpretation, now we have this closed abstract transition system among abstract states that gives us an over-approximate model of what our program can do, right? And so now I have a finite number of paths, but these paths are conflations of lots and lots of different concrete paths, right? And as I explore down these paths, I can build up path conditions that are over-approximate, that are basically the disjunction of all the path conditions that I would have among all of those different concrete executions that some abstract path represents. So then if I build up these over-approximate path conditions, right, and I put them give them to an SMT solver, it can tell me, here's a possible satisfying assignment, or it can say, I've exhaustively proved that there is no satisfying assignment for this, right? And if it can exhaustively prove that there is no satisfying assignment to this, then we know that that's not actually a feasible path, right? And so we can prune it from our model. So it kind of gives us a way to build up a basic baseline model using intentional abstractions that we've designed, but then also to give it more power to refine that model by being able to analyze the path conditions that we would have along these abstract paths and give that to an SMT solver so it can tell us when they're not feasible. And if we have unreachable program states that we determine in this way, we may have among them unreachable contract failures, right? So as I said, these contract systems are basically turning your code into something that has a bunch of assert statements in it, right? These assertions are basic conditionals that say, well, if this property doesn't hold, we'll now raise an error, right? So in the end, there's basically code that has a statement where you're raising an error. And if you can prove that the line of code that raises an error is not reachable, right? Then you've basically proven that it can just be removed from your code entirely. You didn't even need to have it. And if all of the assertions that are produced by a contract can be verified in that way and can be removed, well, then basically the whole contract has been verified ahead of time and can be removed, right? So the idea here is that we might be able to take a piece of code like this that's been annotated with this slow dynamic monitor that actually runs when you run the code and that only tells you that you have an error when it actually hits an error in practice. And we can turn this into an ahead of time verification by using this approach, proving that these are unreachable failures and therefore they can just be removed. So if we verify this, we can remove it. This makes the code simpler and we get basically the best of both worlds, right? Something where we're able to prove that it's correct ahead of time, remove the dynamic monitor so we're not suffering that performance penalty at runtime, and also know that it's not going to fail in general later on. And the reason I think this is such a nice approach is because, again, this dovetails with the idea of being able to do this piecemeal in a gradual way, right? You don't have to prove your specification all up front before you even started writing a line of code. You can write your code and co-design it with your specification and evolve both the code and the specification together with a set of tests, and you can evolve it towards a more complete specification of your code and perhaps towards a more complete verification of your code using this approach. So contracts are a linguistic mechanism for defining these dynamic monitors, and they give us sort of a definition of correct behavior, but they add a significant runtime overhead. And this approach of abstract symbolic execution that some collaborators and I have been working on kind of gives us an approach to verify these contracts on a best effort basis that still degrades gracefully to being able to just dynamically monitor them at runtime if you can't prove it. So we had some experiments that we ran on a set of benchmarks in Racket, and there was almost 50,000, like 49,700 or something like that, almost 50,000 dynamic checks in that 8,000 line corpus of tests. And we were able to verify all but I think 29 of them, something like that. So it was like 99.94% of the contracts we could verify ahead of time. We actually discovered some real errors in that code base when we were running this process. And the ones that couldn't be verified were usually just a little bit too tricky to verify, and with a more sophisticated analysis could potentially be verified. But the really nice thing, again, about this approach is that we can verify and remove almost all of them, and then the 30 or so that are left, we can just leave them as dynamic monitors. So we still get the benefit of contracts and contract checking at runtime for those cases that were too tricky for us to prove ahead of time. That's all I have. Thank you so much. Happy to take any questions.
Time for a couple of good questions. Why do you think for question I have one, so I have to ask you this. So the abstract interpreter would get you from a real state or concrete things into an abstract application. And you've got some desirable things about the abstract one, because then it will enable you to do things in a physical time. But I imagine there may be multiple ways I could abstract things. And so I could have one alpha that's taking this and another gamma that would take me back and so on. It is an abstract, but you may have another abstract which would be a better job. So what is it that you require of this so that they're good?
Yeah, that's a great question. So some of my work in the past has been addressing how do you sort of tune these analyses so that you always get correctness and always get soundness, while being able to vary sort of this compromise between precision and complexity that's being struck. And basically, it kind of breaks down largely into two different kinds of ways of tuning it. One is abstractions for values, and then the other is how precise you're being about the control flow and how many different sort of versions of a piece of code you're analyzing, right? So you can analyze a piece of code over and over and over for different contexts, right? So if you have a function, say, that's called by 4 different callers, you can actually specialize it so that you have 4 different versions of that function, right? A simple way of thinking about this would just be to actually copy and paste the code 4 times and rename them or something so that now you have 4 different versions. Now you can reason about them separately. Maybe in 3 of those 4 cases, you can prove some property, but in the other case, you can't, right? And so that's better than having a conflation of all of them into one one version you're analyzing, where then you can't prove the property that you care about potentially. It also could be the case that if you conflate them, you can't prove a property. But if you distinguish them into 4 cases, then you can prove the property in every case. But it's because in each of those cases, you know something a little bit more subtle about it. So I've worked a little bit on that aspect of it in the past, and I'm very interested in using AI to sort of auto-tune this and figure out how do we come up with abstractions automatically to be able to suit certain program properties that we want to prove. I think that's a really hard open problem, and I think a lot of my work has been kind of going into how do we address that problem using AI without having to give up soundness, right? Because otherwise, if you use some arbitrary machine learning model, it's not sound. But the really nice thing about some of the techniques that we've worked on is that it allows you to use even unsound information as a heuristic to guide the construction of analysis, which then is guaranteed to be sound. So I think that's a very kind of promising approach that I've been working on. Otherwise, I don't have a great crisp answer for you, but I think that's an important problem. Yeah. Mm-hmm. Yeah, good question. That it took about 3.5 hours. So it was not fast. But I would say this was all running in a prototype written in Racket. And I didn't get to talk about it today, but a lot of what we've been working on in my lab is declarative languages that then get compiled down to run on the GPU, basically. And so we are working on how to make analyses like this, something that you can really easily specify at a high level way using just some simple ergonomic rules. And you could say, well, in my programming language, when I hit a state like this, here's how that works. And you could just write that as a high-level declarative rule. And then all of these rules can be compiled down into low-level GPU kernels, which then run in a very high-performance data parallel way. So although we don't have sort of something as sophisticated as this working and scaling well in the GPU, we do have more and more sophisticated analyses that we are running on GPUs that can be scaled up hundreds of times faster than they would run on the CPU. And that 3.5 hours is both on the CPU, on one thread, and running in Racket, which is a very slow language. So kind of imagine running an analysis in Python or something. Yeah.
Yeah, I've got a 2-part question. You mentioned that the phrase "designed by contract" is trademarked. So I'm wondering, are there any real-world examples you can give us or success stories where like a critical system or something, commercial application has used contract verification to work on their software or to design their program? And then the second part is going back to your earlier example of the Toyota incident. Did they end up using design by contract or something similar?
Ooh, I wish I had better examples to give you, but I do know it's a popular approach that's being used in lots of software these days. I'm not sure of like a clear-cut case where there was failing software and then they redid it with design by contract and now it works well. I know the Eiffel programming language, which sort of pioneered this, has often been used for I think power, sort of embedded systems like power systems and things like that. So critical infrastructure, I know it's been applied on, and that's supposedly a success story, but I don't unfortunately know too many of the details.
All right, let's thank Tom again.
Thank you.
Okay, so that was great. I followed this year.